In this video, we're going to talk about section 4.5. Section 4.5. And so what are we going to cover in section 4.5? Section 4.5 is an extension of limits. We covered limits back in chapter 2, but now we're going to talk about limits, and we're going to discuss a more robust way of determining the value of a limit. We're going to bring into play a rule that's developed back in the 1700s. And that rule is going to allow us to find limits using derivatives. That's why we haven't talked about this in the past. So section 4.5 is about indeterminate forms. And there are several of those, and we'll define each one as we encounter them. Indeterminate forms and L'Hopital's rule. All right, indeterminate forms and L'Hopital's rule. So where are we going to begin? Well, we'll just begin with a general discussion of limits. Right, limits, when we saw limits in chapter 2, if we had something like this, the limit as x approaches 1 of 2x minus 3 over x plus 6, the way we would evaluate this limit is we would have used our just plug it in, is how I like to phrase it. I call it the just plug it in approach. That's our first approach to finding limits. We try to plug in 1, and if we don't get something that's undefined, we think to ourselves, well, we're done, and because we are. And so if we plug 1 in here, right, we get 2 minus 3, that's going to be negative 1. If we put 1 in on the bottom, we're going to get 7. And so the answer to this limit problem would be the limit as x approaches 1 of 2x minus 3 over x plus 6 turns out to be negative 1 over 7. So those limits were nice. Those limits didn't drive us crazy back in the second chapter, back in our beginning. But where we started to encounter things that were a little more confusing, perhaps, for some of us, is when we had a limit such as this. The limit as x approaches 1 of x minus 1 over x squared minus 1. When we tried to evaluate this limit using the just plug it in approach, we would plug 1 in up here, we would get 0, right? We would get 0, and then we would plug 1 in down here, and we would get 1 squared, which is 1, minus 1, which is 0 again. And we would be tempted, right? We would be tempted to say this is undefined. But if we did write that down, then our midterm grade wasn't what we were hoping it would be by the time we got our midterm back. Because the answer to this problem is not undefined. If we look at what we have here, right? What we have here, this function, the function x minus 1 over x squared minus 1, if we factor the denominator, right? So this is a bad answer. If we factor the denominator, we end up with x minus 1 divided by x plus 1, difference of 2 squares, times x minus 1. Now, at this point, oh, hey, look, our limit's going to nowhere. So at this point, what we were taught when we were evaluating limits was that we had to pay a lot of attention to the meaning of this. What are we saying when we say x approaches 1? What we're saying is x gets arbitrarily close to 1. There is no distance between 1 and x that is too big. That distance is going to become smaller and smaller and smaller and smaller and smaller. Now, why is that significant? It's significant because what we're asked to do is we're asked to make an algebraic manipulation of this. That's what they tell us in the book. We're going to use algebra. And I just want to recall, take a second to remind you that while algebraically what we did was just cancel these out, right? X minus 1 divided by x minus 1 cancels. And we rewrote this as the limit as x approaches 1 of 1 divided by x plus 1. Then we go back to our just plug it in method. We plug in a 1, and when we plug in a 1, we get 1 divided by 2. Now, I want to go back and I want to address this cancellation here. I want to make sure that we're all completely clear on why we could cancel the x minus 1s. The reason we can cancel the x minus 1s is x approaches 1 means x gets close to 1. And here's the important part, but x never equals 1. And that's very significant. If we're in an Algebra 9 class or an algebra class, and we write something such as this on the board, our algebra students are going to cancel those x minus 1s. They're going to say, well, they're the same thing. I have an x minus 1 on the top, I have an x minus 1 on the bottom. I can cancel those out. In a calculus class, we take that a step further. We remember that you're allowed to divide a number by itself and get 1 for almost every real number. However, you are not allowed to divide 0 divided by 0 to get 1. In fact, that's the whole purpose of this section that we're going to talk about now. So the way we got around that back in the beginning of limits, back in the beginning of the book, is we reminded ourselves that x approaches 1 means x gets close to 1, but it's not 1. What does that mean? It means this is not 0. And it means this is likewise not 0. But they are equal. If they're equal and not 0, then that number, whatever it may be, now that we know it's not 0, whatever that number may be, when that number is divided by itself, we're going to get 1. And that is the important thing that we mentioned, hopefully, many times back while we were learning limits the first time. So, what we could have done back in the beginning of limits in chapter 2 or chapter 1 of your book is we could have done this kind of algebraic manipulation to evaluate our limit and get 1/2. But what do we do if we get something like this? All right, we get the limit as x approaches infinity of the natural log of x divided by x minus 1. Right? It's limits like this that pose a bit of a challenge for us. Back in chapter 2, we didn't really have any methodology, any skill set that would allow us to address a problem such as this. So what did we say, right? What did we say? Well, we didn't say anything because back in chapter 2, they didn't give us a problem like this. So what we're going to do today is we're going to take a look at problems such as this, where in this case we get infinity on the top. The natural log of x goes to infinity as x goes to infinity. Infinity minus 1 is probably still pretty big. We're going to say that's infinity. So we have infinity on the top and infinity on the bottom. What would we do to evaluate that limit? Or is there a way for us to evaluate that limit? Is it possible for us to evaluate that limit? Other limits that, you know, we could do the same kind of thing with, right? We could, back in chapter 2 or chapter 1, wherever we encountered limits the first time, we saw limits that looked like this, didn't we? In fact, we saw things that looked like this even in pre-calc. We had functions. Of course, there was no limit in pre-calc. This part of the problem here was not there. But we had functions such as this in pre-calc. And we were asked, does this have a horizontal asymptote? And in pre-calculus, the way we approach these problems is we say, well, we have a polynomial in the numerator, we have a polynomial in the denominator, and there was a series of rules that we were given that allowed us to evaluate where was the horizontal asymptote of this. And what we said, if you remember, is we said if the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is the ratio of the leading coefficients. In this case, a 1 divided by 2. And we would say this limit equals a half. Now, when we got into calculus, they gave us another approach, right? We were given the idea that you take the greatest degree of the denominator and you divide every term by that. And so we could rewrite this as the limit as x goes to infinity. The highest degree down here is x squared, so we would rewrite this. We would take this as 2x squared divided by x squared plus 1 over x squared. This would be x squared divided by x squared minus 1 divided by x squared. This was our methodology for solving problems such as this when we got to a calculus class. And again, we're going to fall back on that idea that this is 1, right? This is 1. So we're going to rewrite this as the limit as x approaches infinity. That's going to be 1. This is going to be minus still 1 over x squared. We can't simplify that. This is going to be 2, and this is going to be 1 over x squared again because we can't simplify that. Now as x goes to infinity, this is going to 0, and this is also going to 0, and there's our 1/2. We got that in pre-calc by inspection. We got it in calculus by this manipulation. Today we're going to learn another way to do limits such as this. We're going to learn L'Hopital's rule, which addresses problems such as this problem here or this problem here. And so let me take a moment here. Let me clean off the whiteboard, and then we will write L'Hopital's rule out, and then we will see how L'Hopital's rule is going to guide us and help us, to be perfectly frank with you, feel a lot better about evaluating limits. We may or may not have loved limits in Chapter 2, but we're going to love limits once we get L'Hopital's rule. Almost everybody does. So let's write out L'Hopital's rule. It's going to take a little bit of time to get it all written out here, but we'll talk about it as we go. So this is L'Hopital's rule. And what does L'Hopital's rule say? L'Hopital's rule says, suppose f and g are differentiable functions. Now, what do we mean by differentiable functions? Remember, to be differentiable means we're also continuous, right? Differentiability implies continuity, one of the big ideas of Calc 1. And since we're differentiable, we know we're continuous. That means no holes, no jumps, no vertical asymptotes. That's continuity. Differentiable, of course, means no vertical tangent lines, no corners, or no cusps. So we have these two functions and they're differentiable. And in addition to that, we need to put the condition down that g prime of x cannot equal 0. Now I like to pause here and think. Thinking is always a good thing as I'm writing notes. Thinking is a good thing as I'm reading the book. And one of the things that I would suggest you do when you're reading the book is engage with what you're reading. Look at what it says and ask yourself, why are they putting that down? In this case, why are they telling me the derivative can't equal 0? Well, where is it mathematically that we often encounter the fact that somebody can't be 0? And if you're thinking denominator, well, you've hit a home run. Congratulations. Because most of the time when they tell us the derivative can't equal 0, most of the time when they tell us, hey, this can't be 0, it often ends up in the denominator, and that is indeed what's going to happen here. So g prime of x cannot equal 0 near a, except possibly at a. Now, what do we mean by that? Well, we don't care what happens today because we're going to be taking a limit here as x approaches a. So the behavior of g at a is insignificant to us because obviously x is never going to reach a. And then L'Hopital's rule continues. Suppose that. All right. So L'Hopital's rule takes care of two separate situations. And we have to keep in mind that these are two separate situations. So our first situation says, if we take the limit as x approaches a of f of x, our first function, and we get 0, and right, the limit as x approaches a of g of x equals 0. So if that happens, okay, if that happens, if I get the limit of f of x equaling 0 and I get the limit of g of x equaling 0 as x approaches a, or, right, I'm going to change colors here, or, and I'm going to double underline that because I want to make sure we understand these are two separate situations, or the limit as x approaches a of f of x turns out to be either plus or minus infinity, and the limit as x approaches a of g of x turns out to be either plus or minus infinity. Now, I'm going to pause just for a second here to reiterate to you that this is one situation, this is a separate situation. It's not possible for us to use L'Hopital's rule, for example, if f of x equals 0 and g of x equals infinity. L'Hopital's rule does not apply there. We may encounter a case further in this lesson, and we will encounter a case further in this lesson where one of these functions is 0 and the other function is infinity. But the way we're going to solve that case is not a direct application of L'Hopital's rule. We're going to have to do some algebra first, use L'Hopital's rule second. So what we have is if this happens or this happens. To expand just a little bit further on the second case, what happens if f of x is positive infinity but g of x is negative infinity? There we're fine. We're absolutely fine. That's okay. If f of x is negative infinity and g of x is positive infinity, we're all right. We do not have to match plus infinity with plus infinity. Okay, I just want to make sure everybody's clear on that. Now, we've written this with x going to a. This is a two-sided limit. This is also valid if we make this a one-sided limit. It's also valid if this is x approaches a from the right, this is x approaches a from the right, or this is x approaches a from the left, and this is x approaches a from the left. So L'Hopital's rule works for one-sided limits as well. All right? Well, so what does L'Hopital's rule say? It says this. It says then. All right? We always like when we get to the then because we know the good part's coming. It says the limit as x approaches a of f of x divided by g of x, right? Now the assumption here in L'Hopital's rule is we couldn't evaluate this limit in the first place. I mean, if we could have found this limit using some kind of simple steps, we would have done that in the first place. We wouldn't have applied L'Hopital's rule. But L'Hopital's rule says, suppose you couldn't evaluate this. Well, if these conditions are met, this limit is equal to the limit as x approaches a of f prime of x divided by g prime of x. If we always put this down, right? If the limit on the right-hand side. Now, what do we mean by that? We mean this one. This limit right here. If the limit on the right-hand side exists. Okay. So this is L'Hopital's rule. This is how we are going to evaluate limits that in the past may have been a little less kind than we wanted them to be. So I'm going to do some examples. I'm going to leave L'Hopital's rule right here, and I'll work on a couple of examples over here off to the side, right? And we'll start with well, I think it's an example we all have encountered before. We'll take the limit as x approaches 0 of sine x over x. This was an important limit to us back in the beginning of limits. We were told, well, we could prove this with the squeeze theorem. Most teachers say, well, we could prove this with the squeeze theorem, but we're going to let that go. And your job is to remember that that equals 1. And that's a very common approach in a Calc 1 class. We just want you to remember that limit is equal to 1 because, to be honest with you, it's the limit we use more often than not when we're trying to evaluate trigonometric limits. So what would L'Hopital's rule do for us in a problem like this, right? Instead of us having to use the squeeze theorem, or instead of us having to remember the answer, what could we do to evaluate this limit? Well, we could first use the just plug it in process, right? We're going to plug in 0 here for sine. We're going to get 0. We're going to plug 0 in for x, and we're going to get 0. And we know enough to know that that is not the answer. Most often when we evaluate a limit, if we get 0 divided by 0, we know that's not the answer, right? If you look around your calculus class, you'll see some empty seats usually by this time in class. Yeah, why do we have those empty seats? Because those people thought that was going to be 0 divided by 0. That's why we got those empty seats. You're still here because you know that's not 0 divided by 0. So what does L'Hopital's rule say for this? Well, what I like my students to do is I like them to say, well, you know what? I'm going to put an equal sign. I'm going to write an LR above it to let me know that you're using L'Hopital's rule, because this is one of the cases where L'Hopital's rule applies. You have 0 divided by 0. F of x is equal to 0. G of x is equal to 0. That's a L'Hopital's rule situation. So what would L'Hopital's rule say? Well, L'Hopital's rule says this limit is equal to the limit as x approaches 0, right, of the derivative of the numerator, right? It's the derivative of the numerator, f prime of x, the derivative of sine being cosine, divided by the derivative of the denominator. The denominator, the derivative of x, is going to be 1. Now, please pay attention and please take note. This is not the quotient rule. Right? We're not doing the quotient rule. I understand we have a quotient here, and I understand we have derivatives over here. But L'Hopital's rule does not say utilize the quotient rule. It says simply find the derivative of the numerator and find the derivative of the denominator. And if we do that, the derivative of sine is cosine. The derivative of x is 1. And now when we plug in 0, cosine of x is 1. 1, that's the limit of a constant. That's going to be 1, and we get 1. That's the answer our calculus teacher told us we were supposed to remember. So L'Hopital's rule gets us a quick solution to this problem, a lot nicer than what we saw back in the beginning of the calculus book when we were asked to use the squeeze theorem perhaps to prove that. So this is how L'Hopital's rule works, right? This is what L'Hopital's rule does. If we take a look at another example, right? We'll do the limit as x approaches 1. We'll take the natural log of x. We'll have x minus 1 in the denominator. If we plug in 1 here, the natural log of 1 is 0. 1 minus 1 is also 0. So this would again give us 0 divided by 0, which we are not, right? We are not satisfied with that as a solution. We think to ourselves, there's probably an answer to this. Plus, let's not forget the fundamental idea or the fundamental theory when doing calculus homework. We look at the answer in the back of the book first, and then we do the homework problem. Right? You're going to be a much better student if you look at the answer in the back. I didn't say look at the solution. I said look at the answer, right? Stay off of those websites that have the solutions on them until you get stuck. As soon as you get stuck, of course, go look at the solution on the website. But the answer is in the back of your book, and when you look at the answer in the back of the book to this problem, you're not going to see undefined necessarily. And so that gives you the idea that, okay, I have something to do. I like my students to take a look at the answer before they do the problem, especially when we're just starting the section so that we can have a target, something to aim at and go, okay, I'm supposed to get this. Let me see if I can get that. Now, where do we go from here? Well, we're going to use L'Hopital's rule. Why? Because we have 0 divided by 0, and L'Hopital's rule applies to 0 divided by 0. So we're going to rewrite this. We're going to take this. We're going to rewrite this as the limit as x goes to 1. The derivative of the natural log of x, of course, is 1 over x. The derivative of x minus 1 is the slope of the line. X minus 1 is 1. And now when we plug in 1, we get 1 divided by 1, and we get 1. So based on these two examples, the answer to every L'Hopital's rule problem is 1. And if that's the case, we can just stop now, right? All the problems in the book are 1. We'll just solve them all by getting 1, and then we're done. Well, we all know that's not the case, is it? So let's see if we can find another problem and see if we can work out another example here for you. So we haven't done anything where we take infinity divided by infinity yet. So let's go ahead and do one of those, right? We'll fit it right down here. Our example will be the limit as x goes to infinity. And we'll take e to the x divided by x squared. Okay, divided by x squared. Now, if we plug in infinity into this problem, we get e to the infinity. We know what the graph of e to the x looks like. That's our friend the exponential. It just grows without bound. This is our parabola. And as x goes to positive infinity, our parabola grows without bound. So we have infinity divided by infinity. Now, infinity divided by infinity is an interesting case in math because we're never sure what's going to happen. Remember, these are called indeterminate forms. We're not sure what's going to happen. Infinity divided by infinity is not 1. No more than 0 divided by 0 is 1. We're not sure what infinity divided by infinity turns out to be. That's why we refer to it as an indeterminate form. Some problems it may work out to be infinity. Some problems it may work out to be 6. We're not really sure. We have to do the work, hence the name. So we look at this problem. We do our just plug it in. We get infinity divided by infinity. We realize that's a case for L'Hopital's rule. And we think to ourselves, all right, I'm gonna write this. Now, why do I like to write this LR over my equal sign? Well, because I like the greater to have some idea of what's happening, right? If we start with this and our very next line, we write down this. The greater, if we don't tell them we're using L'Hopital's rule, it could be the case the greater thinks, well, they just copied it wrong. But we want them to know, no, we're using L'Hopital's rule. So we've done what L'Hopital's rules asked, right? We took the derivative of the numerator, we got e to the x, the derivative of the denominator, we got 2x. Now we plug in infinity, we get infinity on the top. Instead of infinity squared on the bottom, we have 2 times infinity on the bottom. We still have infinity divided by infinity. Now the wonderful thing about L'Hopital's rule, it doesn't say anywhere up there in blue that you can only use it once. You can use L'Hopital's rule as many times as you need to use L'Hopital's rule. As long as the conditions are met, you just keep applying L'Hopital's rule. So we'll apply L'Hopital's rule again. So now what do we have? We have the limit as x goes to infinity. We take the derivative of the numerator, that's e to the x. We take the derivative of the denominator, that's 2. Well, now we're not going to be able to use L'Hopital's rule for a third time, are we? Because when we evaluate this, the numerator turns out to be infinity. The denominator is the limit of a constant. That turns out to be 2. And so here our answer is infinity. Now, what does that mean to us mathematically? Well, what it means is, it means that e to the x grows much faster than x squared. The exponential grows at a rate much greater than the parabola. While they both go to infinity, if it were a race, the exponential wins that race every single time. The numerator dominated the denominator in this case, and so the numerator gave us infinity. All right. So this is how we address direct applications of L'Hopital's rule. Problems where we have a 0 divided by 0 or an infinity divided by infinity. Fortunately for us, however, L'Hopital's rule brings with it, now don't forget, you can use L'Hopital's rule more than once. If you don't get your answer the first time, feel free to keep using L'Hopital's rule. But make sure, right, make sure that L'Hopital's rule applies. Make sure your numerator and denominator both go to 0, or your numerator and your denominator both go to plus or minus infinity. So I'm going to go ahead and erase this, and then we'll look at some other things that L'Hopital's rule will help us solve. All right. So we called this indeterminate forms in L'Hopital's rule. And the reason we called it indeterminate forms in L'Hopital's rule is because L'Hopital's rule does more. Well, we can utilize L'Hopital's rule to solve other limits than just 0 divided by 0 and infinity divided by infinity. One of those types of limits that we can work with is something that we call an indeterminate product. Now what does that look like? That's how you spell product. What does an indeterminate product look like? Well, it looks like infinity times 0 or 0 times infinity. Now before we just tell ourselves, well, I know what that is, that's 0, it's not. We have a rule that says for every real number a times 0 equals 0, or 0 times a equals 0. That is true. However, infinity is not a real number. So we don't know what infinity times 0 is going to be. Infinity times 0 might turn out to be something other than 0. So when we encounter a problem such as this, a problem that's infinity times 0, what is our approach? What are we going to do here? Right? This would be our f. This would be our g, or this would be our f, and this would be our g. What do I mean by that? I mean, we would be taking the limit, and f would be going to infinity, and g would be going to 0. Or we would be taking the limit, and f would be going to 0, and g would be going to infinity. Now, how are we going to approach, and what are we going to do about solving this? Well, we're going to utilize some algebra, just basic algebra. Algebra 1. If you're wondering why you keep hearing that sneezing, and I'm not saying bless you to anybody, it's not because I'm rude, it's because it's my lab, and I don't tell him bless you. So what are we going to do here? We're going to rewrite this, right, in one of two ways. F times g is equal to one of two separate things. F times g is equal to f divided by 1 divided by g, or f times g is equal to g divided by 1 over f. Algebraically, those are equivalent. Now, what is the purpose of that, right? Why would one go about doing that? Well, if we did that, right? If we did that, what does this equal? Here, f is the infinity, right? So this would be infinity on the top. This would be 1 over 0. Now I'm going to put brackets around that 0 because clearly it's not 0. It's an amount, a quantity that goes to 0. 1 divided by an infinitely tiny number, that turns out to be infinity over infinity, and L'Hopital's rule comes into play. Likewise, in this case, if we algebraically rewrite it in this manner, g is going to 0, so we'd have 0 on the top. On the bottom, we'd have 1 divided by f. F was going to infinity, and 1 divided by infinity, we know that's 0, and we would end up with 0 divided by 0, and winner, winner, chicken dinner, L'Hopital's rule applies again. So our method of solving indeterminate products is going to be to make a choice. It's going to make a choice as to which of these we're going to put on the top and which of these we're going to put on the bottom. Now, that choice is going to come with a couple of caveats, right? We'll talk about that when we look at an example here just in a second. Maybe there's a better way to do this. Maybe there isn't. We'll see. We'll see what happens, okay? So let's look at an example. Let me go ahead and we'll just do the example right over here on the side, all right? So we'll start with the example of the limit as x goes to 0. From the right, and we'll take x times the natural log of x. Now, if we try to evaluate this, we all know what the graph of the natural log of x looks like. The graph of the natural log of x goes like this. As we approach 0 from the right, from this side, we're heading to negative infinity. Obviously, as we approach 0, x is heading to 0. So if we were to just rough this out, this is 0 times negative infinity. And that's one of our indeterminate products. And since it's an indeterminate product, we're going to make a decision. We're going to either rewrite this as f divided by 1 over g, or we're going to rewrite this as g divided by 1 over f. So let's rewrite it. Let's just equals, right? We're not using L'Hopital's rule, so we don't have to tell anybody we're doing that. This is the limit as x goes to 0. And we're going to rewrite this as the natural log of x divided by x. Okay, something like that. Now, I write it and then I pause. Why do I pause? Because my brain is telling me that, hey, Kevin, you've written something stupid. And I'm just trying to think about it and stare at it. And my brain's right. I have written something stupid because that doesn't go there, does it? That's not x. It's supposed to be 1 over x. In this case, I guess we're using this case. So this would be 1 over x. Now, what do? Well, we plug 0 in. Right? If we plug 0 in here, now we're approaching 0 from the right. As we plug 0 in here, we've already noticed we get negative infinity there. As we plug 0, 0 means we're getting very close to 0. 0 is a tiny number. As we approach 0, we're getting tiny, tiny, tiny numbers. Tiny numbers into 1 give us big numbers. So this would be infinity here, and L'Hopital's rule applies. So now we're going to rewrite this, L'Hopital's rule, right? This is the limit as x approaches 0 from the right. We take the derivative of the numerator, we get 1 over x. We take the derivative of the denominator, the derivative of 1 over x is minus 1 over x squared. Now, if we, use some high-powered algebra on this, we're going to get the limit as x approaches 0 from the right. This is going to turn out to be minus x squared over x, which is going to get us the limit as x approaches 0 from the right of minus x. We plug in 0 and we get our answer, 0. Now, I took this example out of the book because why? Well, because I love to take this example out of the book and then poke fun at Stuart's book, because if you're writing a book and you're trying to teach students that 0 times infinity or infinity times 0 are called indeterminate products and hence may result in an answer that's not 0, one would wonder why you put an example in the book where it actually turns out to be 0. Well, I think I have the answer to that. And I'll show you what I assume was the justification for putting this example in the book in the first place. Let's go back and look at the problem, because this problem brings with it a bit of a wrinkle. If we would have readdressed this problem, right? If we would have readdressed this problem, the limit is x approaches 0 from above, and we just rewrite it, x ln of x, right? And we would have, again, had 0 times negative infinity, and we would have said, well, we can't rewrite that. We can't use L'Hopital's rule on that, so we should rewrite it, pardon me. So we get the limit as x approaches 0 from the right. And let's just say, instead of putting the natural log on the top, we would have left the x on the top, and we would have put 1 over ln of x on the bottom. All right. What happens here? Well, if we do this, does everything work out correctly, or is it the case that we get ourselves someplace a little wacky? Well, let's hope it works. Let's see what we get. We get the limit as x approaches 0. We take, now what do we have here? We have 0 on the top, and we have 1 divided by negative infinity on the bottom. 1 divided by infinity is 0, so we have 0 divided by 0. So we're gonna use L'Hopital's rule, right? So we'll put that in here. We left that out. So now when we take the derivative on the top, we get 1. All right, so the numerator turns out to be 1. What do we get in the denominator, right? We take the derivative of x, we get 1. Down here, we have 1 over the natural log of x. So if we take the derivative of the natural log, right, we're going to have to rewrite this. We'll just do some little scratch work off to the side. This is ln of x to the negative 1. The derivative of that's going to be minus 1 ln of x to the minus 2. And then derivative of what's inside is 1 over x. And so what does this look like, right? What does this look like when we get all done? Well, what do we get here? We get negative, right? Negative 1 divided by x ln of x squared. Now, if we use our algebra skills to clean this up, we get the limit as x goes to 0, and we get minus now. And this is actually our numerator, x ln of x squared. Now, if we take a look at our problem that we've gotten from using the steps that they presented us, and we compare that back to the problem we began with, our problem's worse, not better. Instead of x ln of x, now we have x ln of x squared with a minus sign out in front. So this leads us to one of those important little notes that we want to get onto our note paper and not forget. We want to make sure we tell ourselves, if we're using this technique with L'Hopital's rule, we never want to put the natural log in the bottom. We always want to put the natural log in the numerator, which is probably why Stuart put this example in the book in the first place, so we could encounter this problem. If we put the natural log in the bottom, things just get worse. So what we want to remember when doing an indeterminate product is if we pick one of these two directions, right, and we're never really sure, perhaps when we begin, which direction we should pick. Now we do know we never want to put the natural log of x in the denominator. But in another problem, if it does turn out to be worse, right, say we're not working with the natural log of x, or even if we are and we forget that, and the problem turns out to be worse, don't think that it doesn't work. Just go rewrite it the other way. Instead of f divided by 1 over g, go ahead and do g divided by 1 over f. Okay? So that's our indeterminate product approach. So I'm going to go ahead and take a second, erase all of this. All right. So what else can we address in terms of limits that L'Hopital's rule can eventually help us solve? Well, we get something called an indeterminate difference. Indeterminate difference, all right? Well, what does an indeterminate difference look like? Well, an indeterminate difference is something that looks like infinity minus infinity, right? Infinity minus infinity. So what do we know about infinity minus infinity? Well, we don't know the answer is 0, that's for sure. Excuse me. There are problems in the book where you're going to work them out in homework and you're going to get infinity minus infinity and the answer is going to be 0. And then there are other times you're going to get infinity minus infinity. Maybe the answer is going to be infinity. You're never really sure what you're going to get. So when we approach a problem with an indeterminate difference, the typical way that we address an indeterminate difference is we look for a fraction. We try to see, well, let's write down an example. Say we have the limit as x approaches pi over 2 from the left, and we're looking at secant x minus tangent of x. Right? Secant of x minus tangent of x. So when we look at this problem in first glance, we're looking at pi over 2, secant of pi over 2. Secant's 1 over cosine. Cosine of pi over 2 is 0, so this is 1 over 0, so that's infinity. Tangent, of course, is undefined at pi over 2, so we have infinity minus infinity. What I said earlier was true. We take a look at this and we think to ourselves, wow, maybe I should try to find a fraction. Well, where are we going to find a fraction in this problem? Well, there's not a fraction presented to us. Sometimes it is the case that the problem, when we have an infinity minus infinity, there's going to be a fraction in the problem, and we can solve the problem. Our approach then is going to be to multiply by the conjugate. I'm going to write that over here. Multiply by the conjugate. All right, multiply by the conjugate. In this problem, we're not going to try to multiply by the conjugate because if we take a closer look at this problem, right, we've already kind of talked our way into our solution strategy. This is actually 1 over cosine of x minus sine x over cosine of x. Right? There are fractions in this problem, although they're not presented as fractions, they're there. That's a common denominator. We can rewrite this as the limit as x approaches pi over 2. And what do we get here? We get 1 minus sine x divided by cosine of x. Right? So what happens now if we plug in pi over 2? Well, sine of pi over 2 is 1. And so we get 1 minus 1. Cosine of pi over 2 is 0, and we get 0 divided by 0. So here, in this case, we found our solution by getting a common denominator. So multiplying by the conjugate, getting a common denominator, that's how we address the indeterminate difference. Now we're back into our comfort zone. We have L'Hopital's rule here for us. So we're going to write equals. We'll put our L'Hopital's rule sign up here. We're going to get our limit. And we talked earlier about L'Hopital's rule is fine with one-sided limits. So here we go. We've got a one-sided limit. It's no big deal. We're going to take the derivative of the numerator. The derivative of sine is cosine, but we have a minus, so that's going to be minus cosine x. The derivative of cosine is going to be sine. So we get sine x. Now, what does this work out to be? Oh, I'm so sorry. The derivative of cosine is negative sine. So what do we get here? Well, we're going to plug in pi over 2. Cosine of pi over 2, right? If you don't remember, we can always make a quick graph, right? You can always draw cosine like this, and you can draw sine like this. Pi over 2, pi over 2. So cosine of pi over 2 turns out to be 0. Sine of pi over 2 turns out to be 1. It'd be a minus 1 in this case, but it doesn't matter either way because we're going to get 0. And once again, we get an example that doesn't necessarily encourage us to doubt our preformed conclusion that infinity minus infinity is always going to be 0. You're just going to have to trust me when you look at the homework. You're going to find out sometimes it's not 0, right? It could be 0, but other times it's not going to be 0. All right, so that's our indeterminate difference case. Now, where do we go from here? All right. Well, from here, we have our last type of limit that we're going to address in section 4.5. Right? This one is called the indeterminate power. Indeterminate power. Indeterminate powers. Now, what do indeterminate powers look like? Well, indeterminate powers are things like this, 0 to the 0. Now, we know a real number other than 0 raised to the 0 power turns out to be 1. That's the definition we were given back in the day. So we may have forgotten the definition, and we may have just thought, oh, well, since it's raised to the 0 power, it's going to be 1. But that definition clearly states 0 cannot be the number we're raising to the 0 power to get 1. So we don't know what that is. Another thing we're unsure of is what happens if I take infinity to the 0? Same definition. A real number other than 0 raised to the 0 power equals 1. Infinity is not a real number, so we don't know what that equals. And then the last one is 1 to the infinity. We would like to think that if we multiplied 1 together an infinite number of times, we would get 1, but being that no one's ever multiplied 1 together an infinite number of times, we're not really sure what we're going to get. So we're going to call that an indeterminate power as well. So how do we solve these? Well, I think by now you've probably come to the conclusion that L'Hopital's rule is going to have something to do with the solution, but it's going to have something to do with the solution after we introduce logarithms, right? And hey, stop crying. Nothing to worry about. Logs are logs. We can live with them. They're not a big deal. So how do we solve one of these problems, right? What is our approach going to be? Well, let's take a look at an example, and then we'll see how this is going to work out. So what are we going to do here, right? So if we just grab a problem, right, what could we do? We could do something like this. The limit as x approaches 0 from the right, and we get 1 plus sine of 4x, all raised to the cotangent of x, right? That's not something in pre-calc we ever were asked to graph. Thank the Lord, we never would have made it out of pre-calc. But in this class, we are asked, I wonder what happens with this graph as I get closer and closer to 0 from the right. What is my graph doing? Is it going to infinity? Is it going to a number? What's happening as we approach 0? So that's the question we've been asked. If we put 0 in here, we get sine of 4 times 0. The 4 times 0 is 0. Sine of 0 is 0, 1. We get 1. Cotangent of 0. Well, cotangent's not defined at 0. 0 is one of the asymptotes of cotangent. So we get 1 to the infinity. That is one of our indeterminate powers. So how do we approach solving this? Well, what do? Well, we start by introducing a step. We say let y equal this limit. Right, that's what we do. We say let y equal that. And then where do we go from there? Well, where we go from there is we take the natural log of both sides, right? We're gonna take the natural log of this side. We're gonna have the natural log of y equals, and then over here we're gonna take the natural log of this side, right? And what are we gonna get over here? Well, over here we're gonna get the limit as x approaches 0 from the right of the natural log of 1 plus sine 4x all to the cotangent of x. This is what we get. Okay. Now, why have we done this? Well, we've done this because we have an exponent that we don't like, and logs are wonderful at getting rid of exponents. I mean, they don't eradicate them, they don't make them go away, they're not erasable, but we do have that catapult property that says we're allowed to catapult that exponent out in front of the log. So we can rewrite this side as the limit as x approaches 0 from the right. And what do we get? We get cotangent of x times, right? We got cotangent of x times the natural log of 1 plus sine 4x. Somewhere out there in the world, there's a gentleman named Erwin Kramer who I have to give credit for teaching me in college how to make brackets. Thank you, Erwin. Don't know where you are. But in 1983, you see Irvine. So here we go. Where do we go from here? Well, what do? I look at what I have in front of me, and I have the limit as x goes to 0 from the right. I have cotangent, which is infinity, right? That's infinity. And the graph of cotangent, just to remind everybody, we have an asymptote here, and we have an asymptote over here at pi, and the graph of cotangent goes like this, so that's going to be infinity, all right? What happens over here? Well, we have the natural log of 1. That turns out to be 0. We know what to do with this. We know what to do with infinity times 0. That was our indeterminate product case. Now, remember which one you don't put on the bottom? This one, right? We don't put that in the denominator. So we're going to rewrite this as the limit as x approaches 0 from the right. We're going to rewrite this as the natural log of 1 plus sine 4x. Leave that in the numerator. In the denominator, this is going to turn out to be 1 over cotangent of x, right? 1 over cotangent of x. Now, it turns out we happen to know what 1 divided by cotangent of x is. 1 divided by cotangent of x is just tangent of x, right? So what does this look like now when we plug in 0? When we plug in 0 now, we get the natural log of 1 on the top. When we plug in 0 on the bottom, we get tangent of 0. This turns out to be 0 divided by 0. Now, that's L'Hopital's rule. So from here, we can invoke L'Hopital's rule. So we get the limit as x approaches 0 from the right. We have to take the derivative of the natural log of the quantity 1 plus sine 4x. That's going to be 1 divided by 1 plus sine 4x, right? Times the derivative of what's inside. Chain rule, the derivative of what's inside is the derivative of 1. That's 0. The derivative of sine 4x turns out to be cosine of 4x. Times the derivative of what's inside there, so that's going to be cosine of 4x, and then we're going to multiply that by 4, right? And of course, all those are in the numerator. Now, what do we get in the denominator? We take the derivative of tangent. The derivative of tangent, of course, is secant squared x. Now we're hoping that when we plug in 0 here, we're not going to get ourselves into any more trouble. We're hoping we can actually get an answer. Let's see what happens. We plug 0 into here. 4 times 0 is 0. Sine of 0 is 0. We get 1 divided by 1. That's a great sign. 4 times 0 is 0 here. Cosine of 0 is 1. 1 divided by 1, again, a great sign. We have 1 times 4. My numerator is going to be 4. What do we get in the denominator? Well, secant squared is 1 over cosine squared, right? That's really what secant squared is. It's maybe you don't know secant of 0 as well as you know cosine of 0. Cosine of 0 is 1. 1 squared is 1. 1 divided by 1 is 1. We get 1. Now, if we're not careful on an exam, we write down our answers 4. We're happy as a clam, right? We're happy as a clam. But of course, I'm not sure if clams are actually really happy or not happy, so maybe we're not happy either. What do I mean by that? I mean we're wrong. The answer is not 4. What we have to do is we've got to remember all the way back here, we said that the left-hand side was the natural log of y. In other words, what we've come to down here at the very end is the natural log of y equals 4. Our limit is not 4. The natural log of our limit is 4. That's what we've decided. So we have to go one step further, and we have to undo this using the definition of the log, and we get now y equals e to the 4th. We don't want to forget this step on an exam. Nothing more frustrating than walking out on a calculus test thinking you've gotten 100, only to come back in the door and find out you've gotten a 97. Or in my case, a 33. But, you know, that's why they let us teach. So, with that, we'll close. I mean, now that I've made you feel confident in everything I've just presented, we'll close out our lesson here on section 4.5. I will have another video called section 4.5 homework, and I'll work out a few homework problems for you on that video. All right. Thank you for your time.